Thanks, Andre. Right, so this will be a continuation of last time, but first maybe let me regurgitate a bit. Uh, First of all, again, everything I will say is contained somewhere in my mess of a thesis of exactly the same title. Um, and while the thesis is a complete work, the stuff that I will say, especially closer to the end of today, is very much still a work in progress. Progress might be too strong of a word. But anyways, so last time we saw a very explicit example of uh, very roughly speaking, how to well, we saw it in the SL2 case, how the action of a shifted quantum affine algebra arises or might arise on certain kinds of semi-infinite tensor products of certain representations. And the way we saw this last time was we just very explicitly wrote down matrices and matrix elements. And we very explicitly saw that as you take the number of factors in your tensor product off to infinity, a shift will occur in these psi generators of your quantum affine algebra. And remember, these psis are supposed to be the quantum affine analog of just elements inside your Cartan. I'll say a bit more about that later. But the shifts which occur more precisely, this mu, which I've written in red, these are just, in the usual setting, these psis will be power series in either U or U inverse with an invertible constant term. And the shift will make it so that they start either earlier or later than expected. And in general, this mu will be some co-weight which encodes like where each of the generators psi I starts. Anyways, so we saw this very explicitly for SL2 last time. And what I want to do today is I want to explain the geometric origin of this whole collection of objects, starting from a Nakajima quiver variety MQ, and passing to some kind of perturbation of it as a critical locus. And we'll see that that will give a geometric origin for these representations of infinite descending flags with certain asymptotics. And at the end, hopefully I'll have time to say something about the application of all this to the enumerative geometry of curves inside threefolds, which from a representation theoretic perspective will correspond to taking G is equal to GL1 hat, which is slightly more complicated than G is equal to SL2, but not by much, not at a conceptual level, at least. And part of the machinery we'll need for that enumerative application is we'll need to talk a bit about the character theory, Q and QQ characters for these modules of quantum affine algebras, or shifted quantum affine algebras more generally. Okay, so let's get started. Okay. So to get started on the geometric picture, maybe it's easier to think first in the finite length version. So instead of thinking about infinite flags, we'll first start thinking about length L flags, or just more generally length L tensor products of certain representations V of U. So this VL be the length L version of this object, which I've written here. Okay, so these are evaluation representations. We take L of them with the evaluation parameters in a certain geometric sequence with ratio h bar. And such tensor products are very special because they're mostly reducible. Okay, so these are the finite length versions of the things which we'll eventually care about. And so let's first start with the length L tensor product without any kinds of restrictions, no flags, no anything, just length L tensor product. The way to get this from geometry is you take your Nakajima quiver variety of interest, and you make the framing, in some sense, L times larger than usual. And more specifically, what we'll do with this framing is we'll split it up into L blocks, all of the same size. And on the first block, we'll act by a framing parameter u, on the second block by h bar of u, and so on, all the way to the Lth block in this specific geometric sequence. Okay, so this is a reduction of the usual framing symmetry. Usually, the whole framing group is GLW, and that acts on your Nakajima quiver variety. And here we're breaking it down a bit into smaller blocks, corresponding to exactly the product of these groups. And if we call that that smaller group action T, possibly with some extra equivariance. Okay, so the equivariant K-theory of this Nakajima quiver variety will be exactly the L-fold tensor product of the original representation V, okay, with the evaluation parameters in this geometric sequence. Now, if you want to, so like I said, in general, this VL here will be reducible. And so, like I said last time, we're interested in the irreducible factor corresponding to descending flags, as opposed to just arbitrary length L chains. And it turns out that the way to realize this in geometry is to do a small deformation of the original Nakajima quiver variety. But we will do it in the sense of critical loci. Okay? And what that means, I'll be more specific about in 1 second. But what will end up happening is we'll introduce these two extra maps, which are called lowercase xi and uppercase xi. The xi, which is acting on the framing nodes, is not very interesting. It's literally just the choice of isomorphism in between these framing blocks, each of which are the same size, small w. In fact, you can be very explicit about what xi here is, right? Because xi is just multiplication by h bar. And this small xi, which is acting on the regular nodes, will be, well, right now we don't really know what it is, but later these will be the surjections which will form a flag. And so what will happen is we'll end up with a slightly modified space, which is like the moduli of quiver representations like this. Okay. And that space I will write as MQL with this arrow on top. Sorry, I think in my notation I think that was missing. And it turns out that the critical K-theory of this new space will be roughly the module of flags that we want. Okay. So there's a lot of things to explain here. The first thing I want to explain is exactly what this modification of the quiver variety is, and then we'll talk about what critical K-theory is. So like I said, the way we do the small deformation is in the sense of critical loci. So I think it's a good exercise to check that if you start with the usual Nakajima quiver variety, you can actually write it as a critical locus for a certain function on this space, which I've written here. And so what's the space? So if we just ignore this, this small GLV factor here, the resulting space is exactly where the moment map starts. Right? The pre-image of 0 under the moment map for the space without this GLV factor will be exactly the Nakajima quiver variety. And so you can pair that space with a small GLV whose coordinate is this psi from earlier. And this psi is in some sense dual to mu. Mu here is the moment map, sorry. Map. And it's a good exercise to check that the critical locus of this functional here really does recover the original Nakajima quiver variety. Okay. Here maybe I should say that it's important for later purposes that you start with the stable locus of your space of like all quiver representations. And for various stability conditions, you'll end up with various Nakajima quiver varieties. Later, this freedom to choose a stability condition here will be very important to us. Maybe not explicitly in this talk, but certainly important for the entire theory. In fact, for naive choices of the stability condition, we'll end up with the module of flags I mentioned, the one which we're interested in. But for maybe wiser choices of the stability condition, we'll end up with even more interesting things. And I'll say a bit more about that later. Okay. So the first line here is a good exercise. Okay. And so the way we'll get our new module, I'm sorry, I seem to have consistently forgotten to write the less than or equal sign, which reminds us that we're thinking about flags, not just arbitrary chains. Okay, so the way we'll obtain our new moduli of flags is we'll take the old critical function and we'll introduce a new term. And this new term has to do with this isomorphism psi on the framing spaces. And also it has to do with the quiver maps, which correspond to the framing. But specifically what this term is, it's not so important. There are two ways we can interpret this term. The very concrete and very pedestrian way is it's the term which is necessary to introduce, such that if we take the critical locus, it will intertwine this, this new coordinate psi with these framing isomorphisms psi. So the act of intertwining these two is exactly what will create for us this moduli of quiver representations of things of this form. The maybe slightly more highbrow or slightly more abstract way to state this is that this is the most general deformation term, which will preserve this smaller framing equivariance, which we reduced to earlier. This smaller framing group with the framing parameters in this specific geometric sequence. Okay. But regardless of how you want to view it, the net result is that if you take the critical locus of this perturbed function in the exact same ambient space, you will get a moduli of quiver representations which form flags exactly like this. Okay, now, like I alluded to earlier, for certain choices of the stability condition on your quiver representations, those choices of stabilities will force these maps psi to be surjective or possibly injective if you take the opposite one. And for the purpose of this talk and the contents of this talk, that will suffice. That said, hopefully there are wiser choices of the stability condition, which will provide for us not flags of quiver representations, but rather chains of quiver representations which resemble quasimaps to the Nakajima quiver variety. And actually, so here I should say that this whole geometric story is not due to me. It comes from a work in progress by Nakajima and Andre. And I think the original goal of that project, if I can speak for them, was actually to study shifted quantum affine algebras acting on the modular quasimaps. So the hope is that there is some wiser choice of stability which will make these chains into quasimaps. But for now, we'll stick with a very naive choice of stability condition, which will just force all these psi's to be surjective. So we're thinking about finite or infinite descending flags. Okay, so that's the moduli space. And this moduli space, in general, will be very singular. And the correct K-theoretic invariant to think about on it is not the usual K-theory, but instead the critical K-theory. And from its name, you should not be too surprised it's the right thing to take when you have a critical locus. And so what's critical K-theory? Critical K-theory is associated to a function, a scalar valued function on some smooth ambient space. And for simplicity, we'll assume that 0 is the only singular value of this function. Okay, so that all the interesting things happen in the preimage of 0. This isn't a necessary assumption, but it really makes the story much simpler. And so what is critical K-theory of this function phi? So it's the K group of a modification of dB-co called the singularity category. This is originally due to Orlov. I think he first introduced it to study certain Landau-Ginzburg theories. But what it is you start from the usual dB-co, so usual complexes of coherent sheaves, and you mod out by the perfect complexes, the ones which are locally vector bundles. And that's what's called the singularity category. The effect of modding out by the perfect complexes is that the singularity category turns out to be an invariant of just the singular locus of the space of interest. So here, if we take the singularity category of this phi inverse of 0, the singular locus in phi inverse of 0 is exactly the original critical locus, which we're interested in. And so this critical K-theory is capturing some invariance of the critical locus. For those of you who maybe have seen the cohomological analog of this, the singularity category is, in some sense, a categorification of what's called critical cohomology. If you take the cohomology valued in the sheaf of vanishing cycles associated to this critical function phi. Okay. So so that's the K-theory which we want to think about. And rather than doing too many explicit things about it, I'll just state some facts. Okay. The first thing, before we can state these facts, is we have to enlarge the torus, which we think about, by a new variable. And so this larger torus we'll call t tilde. And so what's this new variable? This new variable, again, at a very down-to-earth level, is the weight. It scales this new coordinate psi, okay, this small psi. Maybe at a slightly more abstract level, this new variable keeps track of the weight of the critical function. Okay, so it may be, okay, that the critical functional that you're interested in, phi, is actually homogeneous in a certain variable. Here, for us, if we scroll back and we look at the original potential phi prior to our small perturbation, this original phi, which will define for us the Nakajima quiver variety, is actually not only homogeneous in Xi, it's linear in Xi. Okay. And so this new equivariance will scale Xi and will also be the weight of the critical function. Maybe inverse the weight. Okay. And so we have a larger torus, t tilde, acting on the critical locus of the original function. But it's important to keep in mind that the perturbation which we do to the original function is not of the same weight in Xi as the original function. Okay, so we start off with something which is homogeneous in Xi, and after the perturbation, it's no longer homogeneous in Xi. And so for the critical locus, for the perturbed critical locus, the critical functional is no longer preserved by this extra equivariance, and we can only act by the usual torus, the smaller torus. If we want to think about critical K-theory. Later, actually, though, so sorry, I'm not phrasing this very well. Let me say it like this. The space, which is the critical locus of phi tilde, that space admits an action by the larger torus perfectly fine. Okay, so in the moduli of these flags of quiver representations, of course you can scale Xi by this new factor kappa. But if we want to think about the equivariant, the critical K-theory of that space, we need a torus action which preserves the potential. And so for the critical K-theory, we're reduced to thinking about this smaller regular torus T. And that actually will be very important for us later. Okay, so that said, now that we know there's a larger torus going on, now I can state some facts. Okay, so the first fact is perhaps not super surprising, which is that if we think of the original potentials, one defining for us the Nakajima quiver variety. The critical K-theory of that potential really just is the regular K-theory of the critical locus. And from what I said earlier about the singularity category capturing only invariants of the critical locus, that should not be super surprising. But actually, such an identification is not always true. Here it's to identify the critical K-theory of phi with the usual K-theory of the critical locus. This requires knowing that the critical function is of a very particular form, namely that it's linear in this psi. Okay, this is a dimensional reduction result due to, I'm not sure how to pronounce his name, Isaac. And so the critical locus of the original potential is exactly just the Nakajima quiver variety. So, so we see that in the end, if we take the critical K-theory with respect to the enlarged T of the original potential, we just get these length L chains of quiver representations. Okay. Now, if we now think about the perturbed critical function phi tilde, and we take its critical K-theory now with respect to the smaller torus, we expect that there's actually a map from the perturbed critical K-theory into the original critical K-theory. And maybe in some cases this map is an injection, and probably in most cases it's not. But if we take the image of this map, the expectation is that we'll get exactly this module of length L descending flags sitting inside the L-fold tensor product. You can check this explicitly in the SL2 case. More generally, this is still mildly conjectural. So that was a very brief overview of the geometric origin of these modules. Okay, so they really arise as equivariant critical K-theories of a certain critical locus. Okay. Now, you can run through the entire construction, and you can see that every piece of it is compatible with stable envelopes. So I know that the last lecture was 2 weeks ago, so maybe it's not good to say recall from the last lecture, but I think I'll say it anyway. Recall from the last lecture that these quantum affine algebras or shifted quantum affine algebras, they all arise fundamentally in our geometric approach from stable envelopes, right? From stable envelopes, we construct the R matrix, and from the R matrix, we extract, we reconstruct what the quantum group is. And so all of these critical loci and the passage to equivariant critical K-theory, these are all compatible with these supports and the equivariants for stable envelopes. And so what this means is that the stable envelopes in the larger thing, on the original Nakajima quiver variety, will restrict nicely to the critical K-theory of the perturbed phi tilde. And so what that means is that the original R matrix of the Nakajima quiver variety will restrict to an R matrix for the module which we're interested in, this module of descending flags. Okay. And this R matrix on this module of descending flags, because it arises as a critical K-theory, we'll refer to this as the critical R matrix. And of course, all this is not specific to this this specific choice of like perturbed potential phi tilt. It really is a very general way to get stable envelopes inside critical K theory. Okay, and so once you have these stable envelopes, you can form a critical R matrix. And if you run the quantum group reconstruction process on that critical R matrix, you will get this quantum affine algebra UQG hat acting on these new modules, these modules of length L descending flags. The expectation is that these modules are irreducible for the quantum affine algebra. Okay, so remember I said earlier that that these length L tensor products with the evaluation parameters in a specific geometric sequence, these are usually reducible. And so it's expected that these new modules are one of these irreducible factors. In fact, they're a very special kind of irreducible module. These are called Brushkicking modules for the quantum affine algebra. These are like, in some sense, like the fundamental building blocks of like all other finite dimensional languages. And so like we saw last time, if we now take the length of this chain or the length of the flags off to infinity, a shift will occur in the quantum affine algebra. And the shift occurs because the critical R matrix will pick up certain singularities as L goes off to infinity. And so what ends up happening is you get this mu shifted quantum affine algebra acting on these modules of infinite descending flags, which are asymptotically V. V is an element. Here I should say V, small v is a choice of element inside big V. So your infinite descending flags will be eventually small v. That's this module here. Okay, so that's essentially how the whole geometric story goes. Okay, and it's important to have this geometric story in mind because it will help us when we think about characters of these modules for the shifted or unshifted quantum affine algebras. But maybe before I proceed to that, are there any questions about anything I've said so far?
I'm sorry, what is geometric meaning of this small v?
Of the small v? Yeah, so if we think back to this picture here, right? If you extend the length of this chain off to infinity, what will happen is that, so in the finite length case, imagine you have a flag of quiver representations where each element in the flag is just the small v. Okay? And now imagine you apply a lowering operator to this chain. The lowering operator has to preserve the fact that it's a length L flag, right? And so it can only lower the very last element in that flag. But now if you take the length off to infinity, there is no last element for your lowering operator to actually lower. And so what will happen is that you get a whole bunch of irreducible modules. They're all indexed. They're indexed by what happens asymptotically in your flag. I'm not sure if I can give like a more geometric description than that. Is it okay?
Thank you.
Hope that answered something. Any other questions?
Can you say a few more words about the deformation map?
About the deformation map? Yeah, sure. So very roughly speaking, if we think back to what the potential is like here, here, right? So phi tilde has this extra term in comparison to phi, and roughly speaking, all that the actual deformation map is supposed to do is it's some kind of homotopy which contracts away this extra term. There's a bit of technicality having to do with what equivariance is preserved by such a homotopy, but technicalities aside, that really is like what I mean when I write the deformation map. Is that okay?
Okay, thanks.
Yeah. Okay. So maybe I'll proceed with Q and QQ characters. So Q and QQ characters, well, okay, maybe let's start with Q characters. It's always easier when there's a single Q instead of two Qs. The more Qs there are, the more complicated things get. Q characters are a representation theoretic notion for quantum affine algebras. They are the analog of classical characters for classical Lie algebras and their modules. So we'll start from there. Actually, maybe before we start, I should say the story I'm about to tell about Q characters, that story has been known for a long time. And I have there's zero new stuff about that here. But the story about QQ characters is relatively new. I'll recap a bit about what's known, and then later we'll be able to say some new stuff about QQ characters of these modules of flags which we're interested in, and that will actually be truly new. Okay, so what's a Q character? We'll start with the ordinary character of an ordinary Lie algebra module. Okay. And so at the risk of putting everyone to sleep, I've written it down here, right? So the character of a G module will be, a sum over the eigenspaces for the Cartan. And we'll have something here inside the character, which will record for us the spectrum of the Cartan on those eigenspaces. Okay, so your notation may vary, and it really doesn't matter how you encode these. Okay, so you can pick the favorite way you have of writing these. Maybe you like to write E lambdas or something. But for me, I'll just abbreviate this whole expression as the trace over your module of H. H here is supposed to represent like the entire Cartan. So that's my abbreviation for this whole expression. And in the classical case, these each eigenvalue of an element in the Cartan, these eigenvalues are all scalars, as they should be. Now, for modules of quantum affine algebras, so each element in the Cartan is no longer a single operator. Each element, well, in one way of presenting the quantum affine algebra, we like to think of the Cartan as being generated by power series of whose coefficients are operators. So these psi plus minuses, these are analogs. These are power series in U or U inverse. And these are analogs of the classical Cartan elements H. Okay. So however you chose to package the classical character, I will package the Q character in exactly the same way. Okay, so we'll take the trace over the quantum affine module V of these psi plus minuses. And for a fairly big class of modules, namely the ones inside category O, for some suitable notion of category O, which I don't want to get into, these eigenvalues of these psi's will not just be some power series in U, but actually these power series will be expansions of rational functions in U. Okay, so in the end, the Q character will be some sum over the what's called the loop Cartan eigenspaces of the loop weights, and these loop weights will be rational functions in U. Okay, as opposed to scalars. And so that's essentially what the Q character is in terms of representation theory. For us, or at least for me, because I feel like I'm more of a geometer than a representation theorist. So we will take a more geometric approach to the Q character, partially because it's very, it really, it plays well with the story which I've told so far, and also because later when we define the QQ character, it will be from a purely geometric perspective. So what's the geometric perspective? So imagine that the module you're interested in is not just any old module, but in fact it's the equivariant K-theory of a certain Nakajima quiver variety. And that's not a very special situation, actually. For G finite type, actually, all finite dimensional G modules can be written in terms of these more geometric modules, these equivariant K-theories of Nakajima quiver varieties. So for these V, okay, it's been known for a while, since work by Nakajima, that actually these loop Cartan generators, these psi plus minuses, these operators, in terms of geometry, all that they are is that their multiplication by a certain by the exterior algebra or the wedge of the tautological bundle on your Nakajima quiver variety. Okay, so the Nakajima quiver varieties are roughly moduli of certain quiver representations. So over each point, you can put that quiver representation. And that will roughly be the tautological bundle. You tensor it with a weight U and take its wedge. These psi's will act exactly by multiplication by these things. Okay. And once you know that, it's not so hard to write a geometric formula for what the Q character is. Okay. So here I've written it. Maybe it's not so clear at this point why we'd like to write it this way, but I promise it will be helpful later. So what's going on here? Here I have a Euler characteristic over the Nakajima quiver variety. I've inserted this operator psi, and we'll introduce this extra factor, which one way to think about it is imagine you do localization on the Nakajima quiver variety, right? That means you'll have a sum over each fixed point of blah, blah, blah over some kind of localization weight. And so if you just cancel away that precise localization weight, you'll get a sum over fixed points of this thing which you've inserted. And it turns out that that's exactly what the Q character is. Okay, so the fixed points will form a special basis inside the equivariant K-theory, and this expression turns out to really just be the trace of this operator over that basis. And of course, you can compute trace on any basis. That's the lowbrow way of thinking about this expression. Okay. So that's the Q character. Now let's talk about QQ characters. So what's a QQ character? A QQ character is supposed to be a one-parameter deformation of a Q character. But precisely how to write down what a QQ character is in terms of representation theory, that's actually unknown. It's not so clear how to do that, and that's a work in progress. But for the modules which we're interested in, they come from geometry. And so we can give a similar geometric incarnation of what the QQ character ought to be. And we'll take that as the definition for these modules, these particular modules. So the original definition for the equivariant K-theory of Nakajima quiver varieties, that was due to Nekrasov, who just observed for various reasons that you can take this formula for the Q character and you can introduce a new parameter very easily by just changing this factor, which in some sense for the Q character was extraneous. This term in terms of the tangent space, the tangent sheaf, which was supposed to cancel the localization weight, we can just introduce a new parameter here. And this new parameter we'll call kappa, very kind of suggestively, because we had a kappa earlier when we enlarged our torus. Later, we'll see that these two kappas are secretly the same. Or maybe the same up to an inverse or something, I don't know. So we'll introduce this new parameter kappa, okay? And we'll also symmetrize this wedge. This is kind of a technical point. And it was not present in the Nekrasov's original definition, but I think having this symmetrization here really is the right thing to do. But all that it really does is it twists everything by like a square root of the determinant of whatever's in here. Okay, so it's a mild twist, but it really helps with things. Anyways, not so important for this talk. Okay, so that's what a QQ character is for these K-theories of Nakajima quiver varieties. And right off the bat, we can make two observations. The first observation is, of course, if you set kappa to 1, right, we will recover the Q character. And that's not so surprising. The maybe slightly more subtle observation is that the QQ character is no longer a homomorphism. So here, if we think back to the Q character, that was really supposed to be like the complete analog of classical characters of G modules. And of course, one of the reasons character theory is so powerful is because the character is a homomorphism. Right? If you take the character of V tensor W, it's the character of V times the character of W. This is, of course, true for Q characters as well, but is no longer true for QQ characters. And you can kind of see from this formula why that is the case. It's because, again, if we think of these modules V as being modules of quiver representations, if you want some function to be a homomorphism with respect to the tensor product of two quiver representations, then that function had better be linear in the quiver representation itself. And so if you think about the tautological bundle, that really just is the quiver representation. And so this operator is linear in the quiver representation. And so roughly speaking, that's why the Q character is a homomorphism. But now here in the QQ character, we've introduced this factor which contains the tangent bundle. And unlike for Q characters where that factor just cancels out completely when you localize, the presence of this new parameter means that the actual expression for a QQ character really non-trivially contains this tangent sheaf, all the tangent characters of the fixed points. And the tangent character is quadratic in the quiver representation. It's like V paired with it's like the quiver representation paired with itself for a certain pairing, which will depend on Q plus maybe more terms. And being quadratic will create certain cross terms when you take the tensor product. And so the QQ character of V tensor V prime is not the same as the QQ character V times the QQ character V prime. There will be additional cross terms. Maybe those cross terms can be described representation theoretically. I don't know. Okay. But so one way to think about the presence of this extra term, which is a function of the tangent space, is that if you just ignore this insertion of the tautological bundle, the remaining expression really just is what's called the chi-y genus of the Nakajima quiver variety. Here maybe it should be called the chi-kappa genus or the chi-minus kappa genus. I don't know. And this is an object which is very well studied, maybe non-equivariantly. It's like a thing which encodes Hodge numbers. And so it's very natural to study the same thing equivariantly. And as a generalization of Q characters, it's very natural to include this insertion of the tautological bundle. So that's the QQ character. Later, we'll see even more geometric reasons why it's interesting to study the QQ character. For like G is equal to GL1 hat, these QQ characters will be fundamental building blocks of like curve counts inside threefolds for Donaldson-Thomas theory or something. And they also show up in a lot of other places. Okay. So I've said what the QQ character for the K theory of the Nakajima quiver variety ought to be, but this kind of definition works equally well for the modules of flags that we want to think about, because they're realized in exactly the same way as these modules V, right? So you can plug into this original definition our smaller modules of flags, and all you have to do is you have to replace the original Nakajima quiver variety with our new moduli of flags, length L descending flags. And in fact, we can simplify what's happening in the QQ character quite a bit, because it turns out that this extra factor, this wedge of the tangent sheaf, this is actually very intimately related with a thing called the virtual structure sheaf, which is associated to our critical loci. So what happens is that whenever you have a critical locus, there's a certain deformation invariant version of the structure sheaf, which is naturally associated to it. And in fact, these virtual structure sheaves are not much more general situations where these deformation invariant versions of O can be written down. And for many, many reasons, studying their push forwards, their Euler characteristics is a very productive thing to do. These are like indices. For us, the calculation that you have to do is that these critical loci naturally come with certain tangent obstruction theories, and the tangent obstruction theory for the specific critical loci which we've constructed exactly match. They're essentially of the form like tangent sheaf of Nakajima quiver variety minus like kappa times tangent sheaf dual or something. It's not exactly true, but it's true like maybe up to sign after you take like symmetrized wedge or something. And so if we rewrite the QQ character in terms of these virtual structure sheaves, we get something which is even more natural, even more geometrically natural to study. Okay, these are Euler characteristics of the virtual structure sheaf with a certain tautological insertion. And those of you familiar with enumerative geometry, maybe in cohomology or in Ktheory, probably have seen expressions like this in the past. In cohomology, what happens is you integrate the virtual fundamental class with respect to some kind of insertion. Here we're integrating the virtual structure sheaf in Ktheory with respect to some insertion. Okay. And so here you may wonder what happened to this new parameter kappa, which is like the deformation parameter for QQ characters versus Q characters. This kappa now becomes encoded in geometry. So remember, I said earlier that these new moduli, these perturbed critical loci, these moduli of flags, if you want to study their critical K-theory, you have to take a smaller torus. But if you just want to study the critical locus, the space itself, you can make the larger torus act on it perfectly fine. And what this larger torus will do is it'll scale these maps in your flag, these size. It'll scale them by a weight kappa. And that kappa turns out to be exactly this kappa from earlier, this kappa inside the QQ character. And so we get a very clean, very natural definition of QQ characters for these modules that we're interested in. Okay, so that's all I wanted to say about Q and QQ characters. Before we continue to an actual application to enumerative geometry, I'll pause and ask again if there are any questions.
So is it true that basically, you can do this Euler characteristic on this tautological sheaf, like this T tilde equivalently, and then this.
Yes.
Q. Okay, I see.
Yeah. So here all these expressions which involve this new moduli of flags, we're treating them T tilde equivariant. Yeah.
And this kappa just trivial, like just naturally the equivariant parameter associated to this.
It's naturally the equivariant parameter associated to scaling these. Let me scroll all the way back here to scaling these flag maps size.
Okay.
So of course, you don't have to do these integrals T tilde equivariantly, right? You could choose to forget about the kappa altogether, and that will be the limit where you pass from QQ to Q characters. Yeah, so here if you set kappa to 1, so if you forget about the presence of this extra equivariance, you'll see that the contribution of the tangent character entirely vanishes, and we return to Q characters as we should, right? As we observe here. But for various reasons, it should in principle be much better to study the more sophisticated QQ character where kappa is not specialized to one. We'll see an example of why in 1 second. Yeah. Are there any other questions? Okay, great. I hope I haven't just completely lost everyone. So now I want to return to maybe something a little bit more down to earth for a certain subset of people in this seminar, which is I want to talk about the enumerative geometry of curves inside threefolds. So in the first lecture, I mentioned something about how at least for me, one of the end goals of all this stuff with these asymptotic modules for shifted quantum affine algebras was in its application to Donaldson-Thomas theory and its cousin, Pandharipande-Thomas theory. These are two theories of how to count curves embedded inside threefolds. So in the first lecture, I had some pictures of certain boxes stacked along places. And now we're returning to that picture. So in terms of representation theory, this is the case where G is the Heisenberg algebra GL1 hat. Okay. And so the quantum group that we care about will be what's called the quantum toroidal GL1. Okay. And morally speaking, you can think of this as the quantum affine algebra associated to GL1 hat, even though GL1 hat is not an affine algebra. So here I've drawn a very schematic picture of how I think about this quantum toroidal algebra. Okay, so what does it look like? I've drawn the Cartan vertically. Okay, so the black dots are the coefficients of psi plus, and the red dots are the coefficients of psi minus. The vertical axis is by powers of u. Okay, so psi plus has positive powers of u, psi minus has negative powers of u. Some people do it the other way around. In fact, I think I do too. Not sure why I drew the picture this way. Anyways, so this vertical line is the Cartan. And on the right, we have a whole bunch of lowering operators. And on the left, we have a whole bunch of raising operators. And if you remove every other column of dots, except for the ones immediately adjacent to the Cartan, then you get the picture of UQSL2 hat. So UQSL2 hat has one lowering operator, which will be one column of blue dots. That lowering operator is called E. It has one raising operator, one column of green dots, that's called F. For the quantum toroidal GL1, you just have infinitely many, indexed by the natural numbers. And so of course there will be a Z grading by how far you are along the horizontal axis. So you think that the vertical column, the first vertical column of blue dots removes, sorry, I was about to get too far ahead of myself. This quantum toroidal algebra has a module, has a special representation, which we're interested in. It's called the Fock module. And what's this module? It's the equivariant K-theory of the Hilbert scheme of points on C2. which, you know, if you're a grad student at Columbia working on this stuff, is probably your favorite geometric object on Earth. So C2 has a natural two-dimensional thing acting on it, right? By scaling the X and Y axes. And that lifts to an action on the Hilbert scheme of C2. We'll call those weights X and Y. And so what's the Fock module? What's the K-theory? What's the equivariant K-theory of the Hilbert scheme? It's indexed by the fixed points, or one way to write it is to index it by the fixed points. And what are fixed points inside the Hilbert scheme? They're just usual two-dimensional partitions, lambda. Okay. So the Fock module is an infinite dimensional module with a certain basis indexed by partitions. Okay. And the action of the quantum toroidal algebra on this Fock module is kind of straightforward to describe if you don't care about the coefficients of the action. The first column of blue dots here, this first set of lowering operators, these remove one box from the partition. The second set removes two boxes. The third column removes three boxes, and so on. Maybe they each do this removal process with slightly different coefficients. Okay. And on the other side, the raising operators do exactly the same thing. Like I said earlier, for arbitrary Nakajima quiver varieties, the Cartan psi, the loop Cartan psi, will act on a partition lambda by multiplication by a certain tautological bundle. And maybe I'll be a bit more specific about that later. It's not super important. Okay, so that's the algebra and that's the module. And so now we can consider asymptotic modules, which are our modules of infinite descending flags associated to this Fock module. And so what's an infinite descending flag of partitions? Well, you can arrange them in a chain along the z-axis, which is the only axis we haven't used so far. And it looks roughly something like this. And if you have an infinite chain, if you have an infinite flag, then it's possible that this leg here continues on infinitely. These things are known as 3D partitions in complete analogy with 2D partitions. So for usual 2D partitions, you stack squares in the positive quadrant. For 3D partitions, you stack boxes in the positive octants. And here we'll use the phrase 3D partition to, in a slightly more general sense, where we allow potentially infinite asymptotic legs to extend along the z-axis. You could also have infinite legs along the x and y axes if you want to be more general with our whole setup. But because the Fock module is of finite partitions, we won't have infinite legs along x and y. So we'll only have an infinite leg of profile lambda along z. And the combinatorics of these kinds of 3D partitions underlie one-legged Donaldson-Thomas theory. So it's like one kind of way of counting curves inside three folds. Okay. Now, PT theory has a relative, which is PT theory. And I don't want to get too much into the actual geometry of how these two theories work. Suffice it to say that the combinatorics of DT theory are these 3D partitions with one leg. The combinatorics of PT theory are drawn here. And maybe it's not so clear what's happening here just from the picture. So let me say very briefly what's happening. Imagine you took So these more translucent boxes, these are like the minimal configuration for an infinite descending flag along Z. Okay, so each of these slices is a copy of lambda, and it just keeps on going. And in PT theory, you're allowed to stack boxes in the negative direction. And the way you stack them in the one-legged case is slightly peculiar. And maybe the shortest way to say it, to say what the rules are for stacking these boxes, is you imagine that this infinite leg of lambdas actually extends in the negative direction as well. And the complement of these negative boxes has to form like in some sense, like a 3D partition in the negative direction. So put in other words, if you take slices moving in the negative direction and you look at the complement of these boxes I've drawn, you might have something like, empty, 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 and then maybe you introduce one box, and then maybe a larger partition, a larger partition, a larger partition, and so on. That's the empty space here. Okay. So the complement of the negative boxes inside PT theory form like an ascending chain as you go in the negative direction. Or put otherwise, if you start from negative infinity in Z and you move in the positive direction, it forms a decreasing chain. So in terms of our modules of flags, what we can do to get something resembling PT theory is we can take infinite flags, okay, with respect to this Fock module, and they will again be infinite descending flags. But this time, instead of infinite descending flags starting at 0, heading off to positive infinity, we're going to take infinite descending flags starting from negative infinity and heading off to 0. So maybe here I'll write for clarity. This sits inside the semi-infinite tensor products where we start from negative infinity and then we eventually hit 0. And the evaluation parameters are done accordingly. So like h bar minus 2, h bar minus 1, and then we stop. Okay. So that's how we try to get PT theory from our modules of flags. And crucially, it's important to keep in mind that while for DT theory, we really honestly captured the combinatorics with our module, in PT theory, we had to do this trick of taking the complement, and this will be mildly annoying soon. It's a work in progress to figure out how to avoid having to do this. Okay, so now we have some modules. What do we want to do with these modules? We're going to take their QQ characters. And what happens for the DT module, at least, is we take the QQ character. It will be some kind of Ktheoretic integral over exactly the DT moduli space, whatever it is, okay, of it'll be like the integral with respect to the virtual structure sheaf with an insertion of a certain tautological bundle. Okay, so this univ here is what this was called taught earlier. But in the context of the moduli space associated to Donaldson-Thomas theory, it's more like the universal bundle here, associated to the fine moduli space. So that's what the QQ character of the DT module looks like. And quantities like this have been studied since the inception of like any kind of enumerative theory of anything, really. And these are like the K-theoretic analog of like intersection numbers on your moduli space. These this insertion of this wedge of the universal bundle is like what you do for intersection numbers when you like insert certain cohomology classes into your integral. So on this dt moduli space, we have an enlarged torus, t tilde, acting on it. We have the original x and y weights coming from the Fock module, right? Hilbert scheme of C2. And we have this extra parameter z, which in our 3D pictures really just is the weight of the third axis z. But in our earlier representation theoretic picture, we introduced a new parameter called kappa. Here it turns out that kappa is x times y times z, which maybe from a more abstract perspective, this is the weight of the canonical bundle on C3. Or maybe inverse the weight. It depends on your conventions. Okay. So in maybe more geometric, more enumerative language, this QQ character of this DT module is exactly what's known as the DT one-legged vertex inside equivariant K-theory. And it's the DT one-legged vertex with a particular kind of insertion. I'm not sure why there's a hat here and there's no hat here. I think the right thing to do is to take a hat. Anyways, if you ignore the presence of this insertion and you put no insertion at all, this particular DT vertex really is like the basic building block of like most of DT theory. Like if you know what this object is, then you can compute all DT invariants very explicitly, at least for toric threefolds. Studying this kind of DT vertex is a very important thing to do for not just DT theory, but more generally like the enumerative theory of curves inside threefolds. With an insertion like this, it becomes more complicated, and it's a very hard problem to gain some control, either geometrically or maybe representation theoretically over objects like this. We'll see in 1 second one way of how to gain that control. Here it's worth mentioning that when we take kappa is equal to 1, right, in terms of representation theory, we casted the Q character limit. In terms of geometry, the kappa is equal to 1 limit is what's called the Calabi-Yau limit, because when you trivialize the canonical bundle, get something that's Calabi-Yau. That's how you define Calabi-Yau, a trivial canonical bundle. And so the Q character of our module is what's called the Calabi-Yau limit of the vertex. And so in the Calabi-Yau limit, many things simplify. We've already seen this in terms of representation theory, right? The contribution of the tangent character just completely drops out. And the tangent character as a quadratic function of the quiver representation is like the most complicated part of it all. So maybe here I'll say something a bit more specific for people who know something about DT or PT theory, right? If you imagine like the virtual tangent space of either DT or PT or like any of the theories in this whole family, that tangent character at a particular 3D partition has a linear part in terms of the character of the 3D partition, and then it has a quadratic term. And for many purposes, the quadratic term is really annoying. It really is like the primary source of complexity inside DT theory at a very lowbrow level. And so if you pass to Q characters, if you take the Calabi-Yau limit, that part just completely drops out. and you're left with something which is linear in the character of the 3D partition. That's much easier to deal with. In a very concrete example, if you have no insertion whatsoever and you don't take any infinite legs, okay, so you just think about like regular old 3D partitions. So this would be like an integral over the Hilbert scheme of C3. If you set kappa to 1, basically all the equivariance vanishes and you literally just get the numerical generating series for 3D partitions. So you get something like 1 plus 3 times q plus like, I forget what the next number is, 6, I think, times q squared. Yeah, it really just becomes numerical. It's a very combinatorial object. That said, in the end, I think it's still very important to study the full QQ character. That's what we'll try to do later. Now, if you try to repeat the same story for our PT modules, something goes wrong a bit. Well, not a bit, it really goes very wrong. Because you can try to define what's called the PT one-legged vertex in exactly the same way you define the DT one-legged vertex. Okay, so it'll be like a K-theoretic integral over one-legged PT moduli space with respect to the virtual structure sheaf with some kind of insertion. And that object will not be equal to the QQ character of our PT module. And in short, what goes wrong is that this combinatorial trick of having to take the complement, like imagine you have a function which is linear in X. Then if you plug in the complement, which is like 1 minus X, not much changes. Right? But now imagine you have a function which is quadratic in X and you plug in 1 minus X, then you know some mildly non-trivial stuff happens, and it's not so easy anymore to try to relate that with the original function of X. And so roughly speaking, that's what's happening with this kind of discrepancy. I should maybe stress at this point that this kind of discrepancy is actually not expected in like an ideal setup. Here it really arises because this PT module is in some sense like not exactly the right module to look at. And maybe I'll say a few words about that later. But because the problem only comes from the quadratic part, if we pass the Q characters, that kind of discrepancy goes away. And so it actually is true that the Q character of our PT module is the Calabi-Yau limit of the PT vertex with some kind of insertion. Okay? In fact, you can kind of see what taking complements affects in the insertion. Right? Here we have like a wedge, but here we have a sim. And what's the difference between wedge and sim? It really just is a minus sign. That minus sign comes from having to take a complement. Okay, not sure how much sense that made. Maybe I shouldn't have said that. Okay, so with all that said, I should now say that the comparison of DT and PT vertices is actually a very important wall crossing problem in enumerative geometry. So for example, even without insertions, if you just integrate the virtual structure sheaf, there's a conjecture which says that the PT vertex is a certain normalization of the DT vertex by the no-legged DT vertex. And so, for example, this conjecture is not known for the full three-legged case, but maybe when one of the legs is empty, then you can do some combinatorial argument with vertex operators to show that it is true. And more generally, what happens when you have insertions, even what the form of a relation between DT and PT vertices is, I think even that is like a fairly open problem. And in fact, my original interest in all this asymptotic representation stuff stemmed from wanting to understand, if not prove, some kind of relation like this with non-trivial insertions. Okay, so now that I've said something about the hardness of this problem, now I can finally say a potential approach toward understanding wall-crossing problems like this, which is that maybe instead of trying to control the series, these enumerative series, these vertices themselves, we can recognize that they just come from these modules and try to relate the modules. So this would be like, in some sense, some categorification of these wall-crossing problems. And sometimes it's harder to work with the categorified thing, but here these modules, at least we have some degree of representation theoretic control over them, right? We can say like, okay, there's some shifted quantum affine algebra acting on them. They're highest or lowest weight modules with a certain weight. And so you can do that computation. And what you'll see, okay, so here, what you'll see is that the DT module will be a lowest weight module for a shifted quantum toroidal GL1. And the shift will be a -1 shift. Okay, so here, I guess the notation is not super important. Maybe I'll remind you that in principle, there can be two shifts happening. You can shift psi plus independently of psi minus, right? Maybe psi plus starts at like u -1, psi plus starts at u to the 10 million. But by moving the entire lattice around globally, you can always make it so that psi plus starts at the usual constant term and only psi minus is shifted. So here when I say -1 shifted, I mean that psi minus has been shifted. And if I scroll a bit more, you'll be able to see a little picture of that, right? So psi minus is these red dots, and you'll see that unlike the picture we had earlier, there's an extra red dot here, and that's exactly what this -1 shift amounts to. It means that psi minus starts earlier than usual. So we see that the -1 shifted quantum toroidal GL1 acts on the DT module. It's a lowest weight module with a very explicit lowest weight. The PT module is acted on by the +1 shifted version of the same algebra, and it's a highest weight module with a very explicit highest weight. And perhaps not too surprisingly, the lowest weights for DT and highest weight for PT are inverse to each other. It's not too surprising because if you think about what the lowest weight vector is for DT, it's like the minimal configuration with one infinite leg. And for PT, it's like the analogous minimal configuration with the infinite leg pointing in the opposite direction. So there's some kind of minus sign happening, and the minus sign is reflected in this inverse. Right. So I mentioned this last time, but here maybe I'll say again. There are precursors of these DT and PT modules, which have appeared in previous literature, but they have appeared not as representations of these full shifted quantum affine algebras. In the past, people studied them for a certain quantum Borel sitting inside these shifted quantum affine algebras. And like Andre pointed out last time, also in the past, these modules were studied living over a field. But here, for us, they really live over the equivariant K-theory of the point, which is a much more non-trivial ring. Anyways, so we'd like to relate these DT and PT modules. And I'll say how to do that very briefly since my time is running out. Naively, if you didn't know that these were modules for two different algebras, you would like to say something like, all right, here we have a highest weight module, here we have a lowest weight module, their highest and lowest weights are inverse, they should be dual to each other. That's how duality works. And you can't really do that because these are modules for two completely different algebras. Naively, you might think these two algebras are not too different because it really just is like, how many extra red dots you draw. But qualitatively, shifting by various amounts really changes the algebra by a lot. And so actually the more productive way of comparing these two modules is actually not to compare them for the whole algebras, but actually really to restrict to certain quantum Borels inside these algebras, like all these precursors did. But we have to be a bit careful because the shifted Borel B mu inside the shifted quantum affine algebra A mu changes depending on what mu is. Sorry, Andre, is it okay if I go like 2 or 3 minutes over time? I apologize for this.
Of course, Henry, you can go over time, no worries.
Okay. Yeah, so I apologize to the audience members who hopefully aren't too tired by now.
No, it's a good tradition of our seminar that we go over time when needed, or when there's nothing to say, we just end there too.
Okay.
1:30 is a suggestion.
Okay. So anyways, I promise it won't take more than a few more minutes. Right. So let me quickly say what this quantum Borel is. Okay, it's actually heuristically, it's not so hard to say what it is. You can split the raising and lowering and Cartan series into their positive and negative parts. Okay, so for psi's, we already explicitly have that in the definition of the algebra. For E and F, the positive part is just positive powers of U. The negative part is negative powers of U. And the quantum Borel is just the largest Hopf subalgebra that has nothing to do with the negative parts of all these things. So it's kind of what you might expect. So let me state some facts here. Okay, so if you have no shift, okay, so if this extra red dot were not here, then what are the negative parts of all these E's, F's, and psi's? It'll literally just be the like all the green dots on the negative side of the vertical axis, including the 0 part, and all the blue dots in the negative part of the vertical axis, excluding the 0 axis. And of course, all the red dots. So in the unshifted case, what's the quantum Borel? What's B0 shifted? It'll be the union of the region highlighted in green with the union of the region highlighted in yellow. And you should ignore this extra red dot. That will not exist in the unshifted case. So that region will be the quantum Borel in the unshifted case. Now imagine you're -1 shifted. So now imagine that you, sorry, I think I got my indexing wrong. Now imagine you're 1 shifted, which means you have an extra red dot. Sorry, yeah. You should flip everything I said earlier. When you're mu shifted, you have mu extra red dots. Okay. And so now imagine you're one shifted and you have an extra red dot here. The effect of that is that the one shifted quantum Borel now consists only of the yellow region. It turns out if you try to include a dot in the green region, when you take like the commutator of a green dot with one of these blue dots, that will necessarily involve this red dot, which we don't want to include. Okay, so that's a calculation you can do. And so now, oh, I should also say, if you're minus mu shifted, okay, so imagine if you're minus one shifted, what does that mean? That means not only is this red dot not here, this red dot is also not here. And so, I mean, at that point, it doesn't matter how many red dots you remove. The green and blue dots are stopping you from growing your Borel any bigger. And so mu shifted Borel for negative mu is the same thing as the zero shifted Borel. Okay, so now that we're all quite confused about how mu shifted Borels work, maybe I'll now say how to compare the DT and PT modules. So first we restrict to their respective shifted Borels. So DT lambda will be a module for B minus 1, and PT lambda will be a module for B1. And like I said, B minus 1 is just B0. Okay. So now we have a B0 module and we have a B1 module. And as you can see from our picture here, B1 is a subset of B0. It's a Hopf subalgebra of B0. And so what you can do is you can take your PT module, which is a one shifted module, and you can just induce a B naught module from it. You can just do induction. And that way, now you have two B0 modules. And this induction process does not change the highest weight or anything. So now you truly have two modules for the same algebra, namely B naught. And one is a lowest weight module, one is a highest weight module, and their weights are dual. And so now you can truly say that as B naught modules, DT lambda dual is the induced PT module. Okay. So that's our main result. That's like the representation theoretic comparison of these DT and PT modules. And when you pass the characters, not much changes actually. You can show that even when you take Q characters, this induction process from B1 to B naught, all that it does, it provides no further contribution to the Q character than what's already present inside the PT module. And so all you have to do is you have to multiply by the dimension of the discrepancy from B1 to B naught. And what's that discrepancy? It's this green triangle here. You can see that there's one generator in degree -1, there's two generators in degree -2, three generators in degree -3, and so on. And so the graded dimension of the discrepancy in terms of a variable Q recording that grading is exactly this function here, which practitioners of DT theory will recognize as the McMahon function, which is the numerical generating series of 3D partitions. Okay, it's exactly the Calabi-Yau limit of this DT vertex with no legs and no insertion, which if you think back to the conjectural DT-PT formula, is exactly this thing in the denominator of the right-hand side. So that's a confirmation that maybe we're on the right track to something. And so if you take this relation between modules and you pass the Q characters, you actually get some kind of wall-crossing DT-PT formula. And because we're working in Q characters, this will be for vertices in the Calabi-Yau limit. Now, of course, you'd like to go outside of the Calabi-Yau limit. which actually was the original impetus for even thinking about QQ characters in this context, right? QQ characters allow us to go outside the Calabi-Yau limit. But then if we try to take QQ characters of this relation, of course, we run into the problem of that the QQ character of the PT module is not the PT vertex. And so we won't get some like true DT-PT wall crossing formula in the sense that we expect it. And of course, the underlying problem there is that the PT module is probably not the right thing to think about. This goes all the way back to my remark about choosing the stability condition on the moduli space more wisely. So, you know, one day we'll be able to find the right stability condition, and we'll get a PT module who's with some basis which is truly indexed by like actual PT configurations without having to take a complement. And then presumably one can write down some kind of representation theoretic relation between the resulting modules, and taking QQ characters should produce truly some kind of DT-PT wall crossing formulas for fully equivariant vertices. Okay, so that's actually all I wanted to say. Apologize for going 10 minutes over time. Thanks for your attention. Any questions?
Thanks, Henry. Yeah, how about questions?
So you basically don't have the result for Q characters because like the Q character is not the other characteristic, but what happens if you just like if you compare the QQ characters and just forgetting that they're,
yeah, well,
I mean, you'll get some kind of wall crossing formula, right?
You will get some formula, but it's
Is it of any interest?
It's not so clear what the geometric content of that formula is. At this point, maybe I should confess that you know, after writing the story as I've told it so far from my thesis, I've kind of been taking a break since then. So I haven't thought that much about it yet. But yeah, maybe there's something to be said about the geometric content of that formula. But the only point I'm trying to make here is that it's not precisely the relation between DT and PT vertices that one might want.
Yeah, thanks.
Can we scroll down to this induced statement?
Sure. Scroll down to which one?
This when one module is induced from another.
Here.
Yeah, that's the one, the main result. Yeah.
Mm-hmm.
So I think you made it very clear that you don't have the correct mean. You're not very happy with the
no, certainly not.
No, I think we all got that one. but there should be some module of which the QQ character should be the one-legged PT vertex, right? That's the
yes, that's certainly the expectation.
And so, is there some? Do you think is there some checkable numerical statement between the two vertices?
Right. Yeah. So
looks like this.
Right. Yeah, that's a very good question. Actually, so way before I knew anything about this shifted business, that was actually the one of the first things I tried to do to maybe try to make it as like a first step to maybe making a guess as to what the representation theoretical relationship is. But now a priori, sorry, not a priori, opposite of a priori. Now in hindsight, maybe such a relation is hard to it's hard to verify numerically because of the presence of this dual. And to give an idea of why this is hard, it's because when you take a dual, you like if you take a dual for modules of a Hopf algebra, of course you have to know the antipode. And while in principle you can do that in a manageable way for like maybe the Hilbert scheme of C2, where like the R matrix has like a beautiful abstract formula, which is also okay to work with in practice. Here, these DT modules really are going to be modules for like a more complicated algebra, and the antipode there, I think, is more complicated both in terms of the abstract expression and also in terms of concrete computation. So I mean, maybe it can be done in practice, but it's certainly not something I've tried yet.
Well, how about, can you, in the kind of world of stability conditions, like DT and PT are, more or less extreme. Think you could, is there a way to investigate some other, move the stability condition, not by a whole lot, but by a little bit?
Yeah. Yeah, that's not something I thought about. I think that's yeah, I'm not sure how much I can say about that in real time. Ooh, what just happened? Sorry, I was trying to scroll. If we think back here, back to the incarnation of these modules as critical K-theories. Trying to find where it is. Yeah, so just thinking out loud here. I mean, if we just change if we perturb, like if we move the stability condition across one wall, yeah, I mean, certainly there will probably be a decent description of the resulting moduli. Maybe maybe when you pass the critical K-theory, it's maybe harder to say what happens. Yeah, I'm not super sure. That's certainly an interesting point, and I think it's worth looking into. Yeah.
All right, more questions? Well, we worked almost 2 hours, and so I think maybe at this point well, Henry worked the hardest, and so maybe we'll give him another round of applause. And Henry, don't forget to send me your notes, and we'll see everybody next week, same time. And then the week after, we need to decide what to do. Is if volunteers to speak, that'd be great, or maybe we'll somehow the summer mini courses there's some difficulties in scheduling right now. We'll see what's happening. Right, that's all for today. Thank you, Henry. We'll see you next week. We'll see everybody
for your attention.